future. So today I'm going to present my work on capacity allocation and queuing systems with preferred service start times. And that's my joint work with Tuğçe from Clemson University, and I hope you will enjoy the talk. All right, so before going into the problem, actually, I want to talk a bit about how I got interested in this problem. So one time I was visiting my aunt who lives in a different city, and every time I visit her, she gets very excited and like cooks all the food that I like. So we are having breakfast, and she said she woke up very early that day and she prepared this bread that I like and send it to the bakery to get it cooked, baked, and be ready for the dinner time. So I was very surprised. I asked, like, why did you prepare it that early if we need it for dinner, if we need it for 7 p.m.? And she said the bakery will be very busy around the dinner time. So she figured that there will be other like people who have similar orders. And the timing of the service that day is especially important for her. So she wanted to join the queue early. So this got me start thinking about the queuing systems where customers do not want to be served as soon as possible, but they have a specific preferred time that they want to receive the service, and that affects their queue joining behavior. So some initial questions I had was, in such a queuing system, what is their queue joining behavior? Because apparently they have some motivation to join, to gain some priority, and whether they submit their true preferences or not, because if they have some prior information about the server provider's policy, they may try to manipulate this, right? And more importantly, and also to answer these questions, what is the server provider's capacity allocation policy? So these are the main questions that we want to look at. And in this paper, we are considering the server provider's capacity allocation policy. So, and next, like, why are we bothered with the timing of the service? So when we look at these queuing systems, we see that first come, first service discipline may not be desirable for customer in every situation, or may not be even appropriate for the nature of the service. And when we look at these applications, we see that they are classified as in just-in-time manufacturing, online grocery shopping, catering services, customized services, and time-sensitive products. So some of the specific applications I want to mention are as follows. So the first one is online food ordering platforms, for example, Postmates. So with this platform, you have the opportunity to place an order, to schedule an order sometime in the future within the next 7 days. And as the customer, our satisfaction is measured how closely the provider was able to provide the service to our preferred time. And the next one is scheduled grocery pickup. And this has become a very popular shopping form during COVID, especially. Amazon Fresh and Walmart are offering such services with the promise that they will start picking your orders from the store very close to your pickup time, because no one wants to receive a melted ice cream or a melted frozen chicken, right? And another application is from Homeland Security. In case of an ongoing threat, the police performs like surveillance around the city to identify certain threats. And these could be mainly like the certain gatherings, like the schools, concerts, cinemas, and like any protest or any like immediate gathering that may be happening. And here, if we serve it early, then there may be a false sense of security, but if we are late, then there will be loss of lives. So in these applications, like the timing of the service is important. So hopefully these applications motivate the queuing systems with preferred service start times. And when we look at the literature, we see that most of the related problems are in the scheduling area. And we can divide these into two groups, the deterministic scheduling problems and stochastic scheduling problems. So the deterministic scheduling problems, they consider the time windows, earliness, tardiness, which is something similar to what we are trying to do, but they don't consider the random arrival. So this is what is not existing here. And in the stochastic scheduling problems, they create the entire schedule. That's not really what we are trying to do. And most of the time, they are having a myopic approach rather than considering the overall arrival, but they are looking at like the immediate, like the period. So there's one study that is very similar to ours by Tyagarajan and Rajendran. They consider this like early uncertainty issues in a stochastic environment, but they identify certain heuristics, certain solution approaches, and they compare them in a simulation study, but they do not provide any understanding based on the behavior of the optimal policy. So in this paper, we focus on modeling this problem with like to provide policies for capacity allocation decisions for the jobs with preferred service time in a dynamic environment. We provide some structural results regarding the behavior of the optimal policy. And based on these behaviors, we devise heuristics to be able to find solutions, reasonable solutions in real time. So our problem is a queuing system where each customer has a preference for the timing of the service. We assume that customers arrive independently according to a known distribution. And upon their arrival, customers reveal their preferred service delivery time. And we have a finite number of services that are available in each time period. And we assume that each job can be completed in one period. Customers do not leave the queue, and each job must be served. So based on these assumptions, for every job in the queue, we have two possibilities. Either they will be served before the preferred time, or they will be served on time. So in case of an early completion, the customer satisfaction is decreased. You may be, the server provider may need to hold items until the customer pick up. There could be some holding costs, or in case of a homeland security, you may create some false sense of security. So associated with all of these, we incur early completion costs per job per period in case of an early service. In case of an on-time service, if the jobs that are due the current period, and these are the jobs that have to be served because we don't consider late service, they have to leave the system. If these jobs exceed the available service, the workers may need to work overtime. We may consider outsourcing, or we may simply lose these jobs with a certain penalty. So in that case, we incur a one-time overtime or outsourcing or lost cost. So, and our objective is finding this capacity allocation policy to minimize the long-run average cost. And we formulate this problem as a Markov decision, infinite horizon Markov decision process. So let me mention some common notation I will be using. So M is our service capacity, and K is the length of the customer order horizon. So our planning horizon is infinite, but the customer order horizon is basically how late an arriving customer can place an order. So it is about like how flexible we are towards customers. CE is the cost of early completion per job per period, and CO is the cost of overtime. And XJT is the number of customers waiting in the queue at time T, but they want to be served at time T plus J. So, and our the state definition in the MDP formulation is associated with the state of the current queue. So our state is based on this collection of queues, and YJ is our decision, and YJ is the number of customers who want to be served J periods later, but we are serving them now. So these people are served J periods in advance. And AJT is the number of arrivals we observe at time T who request to be served at T plus J, and PJA is the probability of observing A arrivals at time T who request to be served at T plus J, and J is between 0 to K minus 1 here. So before going into the details of the formulation, let me present this example to show the impact of rolling horizon on the customer preference. So assume that we have a system with 3 periods in the order horizon. So our K is equal to 3. And let's say this is the current state. So it is 2, 0, and 3. That means I have 2 customers who want to be served right now, and I have 3 customers who want to be served 2 periods later. And that is the action I'm taking. So I'm serving these 2 customers who want to be served right now because I have to. And I'm serving 1 customer, 1 job, 2 periods in advance. So that is the early service. And this is how the queue looks like after my service, immediately after my service, but before observing the arrivals in the next period. And now we wait one period, and then in the next period, like time has shifted, and we observe the new arrivals here. And after the new arrivals, that is how my current queue looks like. So simply, when we are calculating the transition probabilities, we are taking care of the updates in the customer preferences as we are approaching to them. So the transition probabilities here are based on how these are updated. And our net reward on state X when we take an action Y is simply the sum of the overtime cost and the early completion cost that we are incurring. And our problem is finding that decision rule delta that minimize our long run average cost. So that's the problem we are dealing with. And the main challenge here is the problem size. So our state space increases exponentially as the number of periods in the order horizon K increases, which prevents us from using these like common solution methods that are designed for such systems like being practical. So this is why we resort our efforts into understanding the structural results, partially for the entire system, partially for small systems, and develop heuristics based on these results. So with that purpose, we now focus on like smaller systems first. So we consider systems with K equal to 2. So customer order horizon is 2, meaning arriving customer can either place an order now or the next period. And this is our Bellman equation to calculate the value function, which is the minimum expected total cost if we have n remaining periods, and we can have n goes to infinity as we are looking at the infinite planning horizon. So if we try to analyze the behavior of the structure of this value function, that's not very easy, but we can do this a little bit better by expressing it through the operator. So we are representing our value function as a combination of two operators, overtime operator and early service operator, as shown here. And instead of looking at the value function as it is, we are trying to understand how it behaves through these operators. So this is one common approach used in analyzing these such functions. So and in our first results, we look at the behavior of these operators, overtime operator and early service operator. And through lemma 1 and lemma 2, we show that if we have a function f of x, which is increasing and component-wise convex, then our both overtime operator and early service operator, they are also preserving the same properties. They are also increasing and component-wise convex, which implies our value function for k equal to 2 is also increasing and component-wise convex. And that results leads us to the first theorem, which shows the monotonicity of the optimal policy. So the theorem states that if we have a system with two periods in the planning horizon, k equal to 2, but with any arbitrary service capacity, any cost, and so on, the optimal number of jobs to be served is monotone in the number of jobs in the system. So therefore, the optimal policy is of threshold type. So this result is important because now we have more information about the structure of the optimal policy, and we can look for that structure. So that's our first result. And the second theorem is for general systems. And here we show that for any system with arbitrary number of periods in the order horizon, capacity, and cost, in the optimal policy, if you are not serving one queue entirely, then you should not serve any queue that is associated with the later periods, later preferences. And this theorem implies a cumulative threshold. So apparently, like for the entire system, we have some cumulative threshold, and we will be using this in our this solution methodology design as well. All right. So now we are focusing on the threshold policy. So how it works is, if we have thresholds, optimal thresholds or like heuristic thresholds, then we can calculate the associated actions for these thresholds. And this is how it works. So given a threshold for every q from j to k minus 1, and considering any state, we calculate the excess number of jobs in the state with respect to the threshold, and we try to serve them as long as we have remaining capacity. So let me present this example. So here we have an example with k equal to 5. So we have 5 periods in the order horizon, and our capacity is 8. So if this is the threshold I'm using, and if this is the state I'm considering, the first thing we do is calculate the excess number of jobs in each queue. And starting with the most urgent one, which is this, we serve these excess jobs as long as we have capacity, and we update the remaining capacity at every state. So here I have 1 remaining capacity, but I have 2 excess. So I can only serve one of them, and the remaining actions will be equal to 0. So that is how the threshold policy is implemented. And now we go back to the small system again, and we calculate the optimal exact thresholds. So here we are considering a system with 2 periods in the order horizon and with a single capacity. And for arbitrary early service cost and overtime cost, we calculate this optimal threshold. So here we have 3 brackets because our capacity is a unit capacity. So for example, here it says, if the early service cost is very high, then your threshold is A, which is the maximum number of arrivals. So there's no way that you can exceed that with this threshold, meaning that you will never serve early because it's very expensive. If the overtime cost is very high, then the corresponding threshold is 0, meaning that whenever you have remaining capacity, try to serve the jobs because that overtime is very expensive. We are trying to avoid. But in the middle region, it's determined based on the relationship between early service and overtime cost. And this phi here is represented as a function of the arrival probabilities, and 1 over phi can be interpreted as the measure of risk of incurring overtime. Because when I'm serving a job early, I know that I'm gonna pay early service immediately there. But if I wait, then that job, there's a risk that that job may fall into overtime. So these thresholds are calculating like when these breaking points. All right, so now we have the optimal threshold structure for small systems, and we are using this structure to develop solution methods for our general system. So these are the steps of our heuristic development. So what we do is, given a general system with arbitrary number of periods in the planning horizon, number of service and cost, so we create a projection of the original system where we only have 2 periods in the planning horizon, but all other parameters are equal to the original system. And then for this projection, we calculate the thresholds, assuming that we only have 2 periods. So if we have single capacity, we calculate the optimum threshold. If we have multiple capacity, we calculate the local optimum threshold for k equal to 2. And then in step 3, we take this threshold for k equal to 2 and we extend it to the original system. And this is how we have the first thresholds. And these thresholds, or the actions that are suggested by these thresholds, may not obey the optimality conditions that we found earlier with theorem 2 and with some other results we have in the paper. So with the last step, with step 4, we determine the actions that are suggested by these thresholds. And if there are any suboptimal early services we notice, we remove them. And then we reallocate the total services obeying theorem 2, and that is the first policy that we are generating. And we call this threshold TH heuristic. So that's the first one. And our next heuristic uses the threshold TH heuristic as the initial policy, and we implement one-step policy improvement for the policy iteration algorithm, and that is our second heuristic. So this is called threshold with one step TH1S heuristic. So as you can see, there's a very immediate connection between TH and TH1 step. TH1 step will definitely improve the optimal solution, but at the expense of additional computation time. And we compare our heuristics with many benchmark policies. So these are the optimal policy. The next one is called never early policy, and E, it never serves early. And the other one is uses the never early policy as the initial policy, and then it implements one-step policy improvement. So it is never early one step. The other simple benchmark is serve all. So it always serves early, tries to serve early whenever there is capacity. And the next one uses the serve all as the initial policy and implements one-step policy improvement. So these are the 5 policies we are comparing. And our comparison basis is the deviation from the long run average in terms of like how close we are to optimality, and the computation time in seconds. And we use the Poisson distribution to model the arrivals with rate lambda. And we truncated to Poisson with the maximum number of arrivals A. And for given a general arrival rate, we are calculating the arrival rate for every J. These are the requests for different periods in the planning horizon, as shown here. And we also experiment on different customer order patterns. So we have this K periods in my planning horizon, order horizon, but customers may have different preferences, right? So if customers are equally likely to request a job for any period in the planning horizon, order horizon, we call this equally loaded systems. In some systems, customers may be more likely to request a service early in the order horizon. These are called front-loaded systems, or just the opposite. They may be more likely to request a service later in the planning horizon. These are called back-loaded systems. We may consider random loads or peak loads as well, where the preferences are distributed by triangular distribution over the order horizon. So here, you can see the change in the probability. So these are the probability of a customer requesting for any period in the planning horizon. So for example, with the front-loaded system, these are more likely to request for the early services, but very unlikely to do it for later services. And for the back-loaded systems, most of the existing jobs are appearing in the late periods in the planning horizon. Okay. And these are the parameters that we have tested on, but I will just present a subset of our computational results. And our computational results provide insights about how the optimal policy changes and how the performance of the heuristics changes based on different scenarios. And the main scenarios we are considering is the customer order pattern that we capture through the load of the system, regarding the sensitivity of the system, whether it is customer-centric or server-centric based on the ratio between the early service cost and overtime cost. If early service cost is high, this system is customer-centered. Otherwise, it is server-centered. And about the flexibility of the ordering system, if K is long, then we are giving more flexibility to customer to place an order, but we are making things difficult for us to be able to calculate and manage. And finally, the server capacity of the system. All right, so the first set of results I'm going to present is about the effect of the order pattern. So here we have the results for all these the solution methods, optimal, R, heuristics, and other benchmarks for different loads, equal load, front load, back load, and peak load. And for different number of arrivals, Z is the objective function value, and T is the computation time, and %D is the deviation, average deviation from the optimal policy. And these are our parameters for this experiment. And what we see here is that our threshold one step finds the exact optimal solution in all of these instances. Serval one step performs very well indeed, and it finds the optimal solution in all but just one instance. And our threshold heuristic, so considering these heuristics that don't perform the one-step policy, these are our threshold, never early, and serval. Our threshold heuristic outperforms all others. And among these, our threshold one-step heuristic outperforms all others. All right, and the next experiments are about the impact of the early service cost. So taking these parameters, we increase the early service cost from 5 to 10. So that's the only change in these experiments. And again, our threshold one step finds the optimal policy in all cases, and serve all one step also does the same thing for this case. And our threshold again outperforms all other simple heuristics that are without policy improvement. And notice that from front load to back load, these heuristics, the never early and serve all, they are myopic and they cannot capture the impact of the load, because with the front load, even if you are myopic, you are able to see them. But with the back load, most of the order, like your system may be crowded, but these heuristics or these policies are not able to capture it. So their performance is getting much worse as the load in the system is delayed. And we see that as the early service cost increases, never early policy improves, because for obvious reasons they are avoiding early service decisions, and serve early gets worse because they are performing a lot of early service. But again, like we find the optimal in all of these. And in the next result, we increase the number of periods in the planning horizon. So now k is equal to 5. And this is actually the largest order horizon we can consider. After that, we are not able to calculate the optimal policy. So I'll talk about this in a bit. But when k is equal to 5, you see the increases in the computation time. So now we are talking about like 4,000 seconds for the optimal policy. But again, we can find the optimal policy again using our threshold one step or serve all one step. And we can do that with 75% decrease in the computation time. And as k increases, again, never early and serve all heuristics, these policies, they can't perform well with respect to like others. And again, considering these heuristics without one step policy improvement, our threshold heuristic outperforms the others. And in the next set of calculations, we consider larger instances. And again, these are the instances where we can't really perform any policy improvement due to the computational limitation. So we are limited with these 3 policies only. Our threshold heuristic, never early and serve all. And we are operating with a maximum 40 arrivals for one period. So this could be 160 arrivals for k equal to 4 in a single period, 20 servers, and these are the cost. And we are experimenting on different arrival rates for different loads again, equal load, front load, back load, and peak load. And we calculate the long run average cost. And we also calculate the confidence interval, 95% confidence interval. And here we are comparing never early and serve all with respect to our threshold. When we see that never early deviates by 25% from our threshold, it is 25% worse than ours, and serve all is much worse. So our threshold heuristic is the one that provides significantly better objective function values, but on the other hand, obviously that comes at the computation like a longer computation. So we are taking like 15 minutes to calculate these. Right. So let me summarize our computational results. So what we see is, if we are dealing with easier systems, and these are the extreme systems in terms of like the cost parameters or the capacity. For example, for the cost sensitivity of the system, if the system is highly customer sensitive, meaning that early service cost is very high, or server sensitive, meaning that overtime cost is very high, then the decisions are kind of obvious. Either we will serve on time or serve early. And in terms of the server capacity, if the capacity is very limited, there's not much you can do anyways, because you will most probably be operating at overtime. And when the capacity is high, and again, there's not much to decide there because you have large capacity to be able to serve everything pretty much on time. But these are not the common systems, right? These are extreme systems, but most of the time, most systems are operating in this moderate regions where these heuristics are not performing well. but our threshold one step finds the optimal solution in all cases where we can calculate the optimal solution, where we can actually perform one-step policy improvement. And as the problem size increases, and again, there's a significant cost in terms of computation. So our threshold one step finds the optimal policy. And for larger instances where we can't even perform any policy improvement because of the computational limitation, we are limited with threshold, never early, and serve-all heuristics, and our threshold finds the best policy in terms of the long-run average cost. So what we have done in this paper is considering these queuing systems where customers have a preferred service start time. So they don't want to be served immediately, but they may have an incentive to join the queue early to gain certain priority. So we model this problem as a discrete time infinite horizon MDP, and we develop some structural results, and based on these structural results, we devise heuristics for larger systems. And we observe that through the computations, we can find, like, whenever we can find the optimal solution, our threshold one step finds the best solution, like finds the optimal solution in much less computation time. But whenever that's not the case, our threshold heuristic finds the best solution among all available benchmarks. So what we are currently working on, what we have done in this research stream, is that we are considering systems with different types of customers. And we are also considering that as the customers wait in the queue longer, their priority increases, because this is how we can capture their customers' incentive to join the queue early to gain priority over other customers. And we are also looking at more general systems. So this is from the perspective of the server providers. On the other hand, we are also looking at the customer behavior. So considering this system, what is their queue joining behavior? So in certain cases, they may have a cost, internal cost, to join the queue early. And again, based on the information they have about the server provider's policy, do they submit their true preferences, or do they try to manipulate this? And next step, if this is the case, what will be the game theoretic approach from the server provider's perspective to develop this policy? All right. So that is pretty much what I wanted to present today. Thank you very much. I will be very happy to answer any questions if you have any. And our paper is recently available in NRL if you want to access the full paper, so you can do that through this link. Thank you.